All right, so let's start our lecture over 7.5 by trying to find an angular equivalent for Newton's second law. We know that Newton's second law is equal to F equals ma, and so we might say, well, torque is equal to mass times angular acceleration, but it's not quite that simple. There's actually a angular equivalent for mass as well that we have to find here. So if we look at this drawing here, and you can go ahead and sketch this in on your drawing if it's not there, I think it should be. What we have here is a particle mass that is attached to a thin rod, so a rod that doesn't have any mass, and is being swung about in a circle. Because this is happening and it's traveling in a circle, there is an acceleration directed in because there is a force centripetal due to tension. And this centripetal acceleration causes the object to change directions, right? But the thin rod is also speeding up, so there is an acceleration directed at 90 degrees to the radius, and this is a tangential acceleration, which means that there's also a force directed at 90 degrees and to the radius or to the distance from the pivot, right? Because it's moving about in a circle. And so therefore there is a torque going on, and the torque is going to be based off this acceleration right here, because this is the one that generates a force at a 90-degree angle to the distance from the pivot, right? And we said that when that happens, we generate a torque. So let's go ahead and look at where our angular Newton's second law is going to come from. So if we write Newton's second law in a linear or translational form, what we can see is F equals ma, but I'm going to call this acceleration tangential, right? And we can go ahead then and let's rearrange this into A tangential is equal to F over m. And from there, we can now take, and remember we had equivalents for translational motion or linear motion to get to rotational, right? And we said that acceleration is equal to alpha times r, right? We just take the angular equivalent multiplied by r. So let's go ahead and sub that in right here. For AT, whoops. That's kind of rough looking. Let me rewrite that. And then we'll go ahead and solve for angular acceleration. Divide both sides by r. All right, and we are part of the way there. So just by making that substitution right here of this in for there for acceleration, alpha r, and we now see that alpha equals F over mr. All right, but this still isn't quite going to be good enough because we said that there is an angular equivalent to force called torque. So we need to deal with that, right? So we can go ahead and remember that torque is equal to R cross F, right? Which is also equal to RF sine theta. And in this case, theta is going to be 90 degrees. Sine of 90 is 1. So we don't have to write the 1. So we have here torque then is equal to RF, but we want torque in here, right? And we don't want F there, right? So I'm going to go ahead and solve for F now. So if I rearrange this, I can see that force is equal to torque over R. Okay. So now I can go ahead and sub that right there. And we can go ahead and rewrite this then as alpha equals torque over mr squared. And so this is Newton's second law for angular motion. And if I rewrite this one more time, I think maybe it'll make a little more sense, because this is in the form A equals F over M. So it gets at this idea, well, what the heck is this, right? This is replacing mass, and we call that quantity there mr squared. Let me go ahead and rewrite this one more time. If I just rearrange this, right, into this form, F equals ma, right? So then I would have to multiply both sides by mr squared to get torque alone, right? So I'm saying it's going to be torque equals alpha times mr squared. And so what I'm trying to say here then is that this quantity right here is our angular equivalent for mass. And we call it moment of inertia. So I is equal to the moment of inertia, and we're going to call this quantity I. So, and it's equal to mr squared for a point mass. So that is that I is also our angular equivalent for mass. Let me go ahead and straighten that up a little bit. All right, so what we have here, what I could have rewrote this again as then is torque equals alpha I, right? And so both of these, well, this is technically Newton's second law. Angular, right? All right, so what we have here then is angular force is equal to angular acceleration times angular mass. And mr squared is the angular mass of a particle mass. So when all the mass is located at one point, which isn't always the case, but it can be, right? And so what's something where it wouldn't be the case? Say, for instance, if I had a meter stick. Then I would have the mass is at multiple points, and it's actually at an infinite number of points, right? And instead of being just in the center, although we like to assume the center of the meter stick is at the center of gravity. So we'll kind of talk about that here in a second. All right, so hopefully this is making sense. F equals ma, torque equals alpha I. I of a particle mass is mr squared. If it was something like a meter stick, it would depend how it was rotating. If it's rotating here at the center, the meter stick's moment of inertia is 1/12 ml squared times the length of the meter stick. If it's rotating here at the end like this, it's actually going to rotate different than if it rotates here, right? It's easier for me to rotate a meter stick like this than it is like this. So the moment of inertia is actually greater here. And that's what we're going to look at here. It's actually 1/3 ml squared instead of 1/12 right here. Now, why is that? Because if we think about this, right, and we go back to the form up here, which is alpha equals torque over I, we can see the relationship, right? It is easier for me to accelerate the meter stick right here because its moment of inertia is smaller, right? When this number is smaller, alpha is larger. When I hold it out here, the moment of inertia is greater. it is harder with a larger moment of inertia, the angular acceleration, how quickly it'll speed up or slow down around a pivot is actually going to be less. So yeah, that's kind of where we're going with this in our goals here. So all right, so Newton's second law, angular equivalent for F equals ma. Okay, let's go ahead and flip this page over. All right, so you should have this as well on your note guide already drawn in. And if you don't, you can pause the video and draw this in. What I have here is an object that's drawn as an extended object. And the idea of in physics, what we had going into this unit was we thought of everything as a particle mass, that all of its mass was at one point in the center of the object, right? But that's not sometimes true, and it's not sometimes a good, it doesn't always work, right? So what we need is this idea of an extended object where we can think of a mass as involving multiple points. I think an example of this would be if and I know I did this in some videos I made last year, where I took a weight, it was a tennis ball, but let's say I just taken a mass, if I had a 100-gram mass or something, and tied them to the end of the meter stick, right? That this meter stick behaves differently if I was to attach the masses here, or if I was to take those two masses and attach them here. And this is kind of the same idea here. So what explains this is moment of inertia, right? The reason this acts differently here, say, than there. So we can't use this particle idea that a mass is just a particle of its total mass all the time, right? So here then, for instance, in this case, we have this object that's going to consist of its mass acting at 3 points, M1, M2, and M3. And so as it rotates, if it's rotating this way and speeding up, right, then it's gonna be caused by a torque, a force on all three of these masses about this axis of rotation. Now, where the axis of rotation is matters, right? I just said that with a meter stick. If I rotate about the middle, it's different than rotating about the end, regardless of where the masses are. Meaning if the masses were attached to a meter stick out at the end, right, and I rotated here, it's still going to be a different moment of inertia than me rotating here at the end. So the rotation axis matters, right? Right now it's right here at this point. And another reason you could see it mattering is this. If I was to move this rotation axis, look at where M1 is. Would R1 change if I move the rotation axis, say, to right here at the very bottom, right at this point? You should say yes, right? Because now R1 is larger. And so the torque that F1 creates, torque is equal to R times F times sine 90, right? Sine 90 didn't change. We'll say this is still a perpendicular force, but we now see that R1 is larger. So there would be more torque being generated by this force because torque equals RF sine 90. All right. So anyways, the idea here is that there's going to be a net torque generated by each mass, right? Each mass is going to have a different distance from the axis rotation, but all three masses will have the same angular acceleration. And that should make sense. For instance, if you were on a merry-go-round and you sat, I don't know if I can draw this. All right. And you sat like out here and your little brother sat near the middle, that even though you guys were sitting in different places, you would still sweep out the same angles in the same amount of time as you sped up, right? Your angular acceleration, your angular velocity would be the same, and your angular velocity would change in the same amount of time, because as this turns, everybody that's on the merry-go-round goes through 360 degrees in the same amount of time. Everybody speeds up angularly in the same amount of time. What isn't the same is your linear velocity, right? Because you're sitting out here, you're braver, you're traveling a larger distance in the same amount of time. So your linear velocity would be greater than your brother's, but your angular velocity would be the same as your brother's. So all three of these points have the same angular acceleration here. They're all speeding up the same due to this force, right? This force at 90 degrees, which creates a torque, causes an angular acceleration. Why do torques cause angular acceleration? Because torque equals, instead of F equals ma, we can say torque equals I alpha. So a torque causes an angular acceleration. All right, but anyways, this idea of I here, right? Well, what is the moment of inertia of this object? Well, when we have an object like this, which is an extended object, right? This is an object where its size and its mass in different locations matters, right? That we can't consider it just it's all of its mass at one point. We have to consider its mass acting at multiple points. That's the idea of an extended object. Well, its torque is going to equal, its net torque is equal to alpha times the I value of all 3 points. And why does this matter? Well, we can then say that we can just add the torques together, right? The moment of inertias together. I is equal to m1 r1 squared plus m2 r2 squared plus m3 r3 squared. And we get the sum of as many masses and as many distances from the axis of rotation that we have, right? It's pretty simple. This works really well if an object is composed of just 3 points, right? And that shouldn't be a problem. But you can see where it might get a little tougher, right? For instance, if I go back to this example, well, let's rotate this, say, about this meter stick with 2 masses attached. Maybe this is a 100-gram mass, and this is a 100-gram mass. And this will be the axis of rotation. Whoops. All right, well, we can see that if we were to if we were to use this logic, that the moment of inertia total, right, that I total is equal to we'll say I100 plus I100 plus I meter stick right? That we can get an I total here, right? And it wouldn't be that bad, because I total, we can think of these masses as being point masses, right? So a point mass, I'll just write the okay, I'll just put an arrow here and say this is a point mass. A point mass has the formula mr squared, right? Where it's the mass of the object, 100 grams in this case. I'm going to go ahead and change it to kilograms, or I'll do it in a second, right? Is equal to mr squared plus mr squared plus I meter stick. I'll come back to that one in a second. All right, so a point mass has mr squared. So I total then is equal to its mass, which is 100, so I'll change that to 0.1, times the distance from the axis of rotation, which we'll just call it, we can call this, we'll call this R, but I'm going to express it in terms of the length of the meter stick. Maybe if the length of the meter stick is L, right, I'm going to call this L. Why don't we call this equal to 1/2 L? Sound good? We could have just called it 50 centimeters or 0.5 meters. I understand that. I guess we could if you really wanted to. It doesn't really matter. I'll call it 50 centimeters. I'll call it 0.5 meters. All right, you get the idea, squared. So for this mass, it's going to be the exact same thing, right? All right, and finally we're getting this idea of the meter stick. And this is going to cause a problem, right? Because you might say, well, the meter stick, let's say it has a mass of 200 grams. I'm just making that up. 200 grams. And you might say, well, it's the axis of rotation is right here. But what's the meter stick's distance from the axis of rotation? And you might say, well, its mass is acting at center, so its distance is 0. And then therefore, I meter stick would be 0.2 times 0 squared. You're telling me that this has no moment of inertia? This mass that's got a weight here and a weight here and a weight here and a weight here has no moment of inertia? That's ridiculous. That wouldn't work, right? So what we have to realize here is we actually have the meter stick has a mass here and here and here and here and here and here, and you might say it has an infinite number of points. And you know, how do we deal with an infinite number of points that all have a moment of inertia of mr squared, right? And so we have these tiny masses, right? Infinitely small masses that have a moment of inertia. So what we have to do is we need some calculus, right? We need some way of dealing with infinitely small masses that all have a moment of inertia of mr squared. And we need to add all these up. So this is a job for calculus, for an integral, and to add up all these infinitely small masses. And since we don't know calculus, or most of us don't, what we'll do is we'll just go ahead and say that the moment of inertia of all of these masses of a meter stick, we'll just look it up in a book, right? And so on in our chapter, and I forget what page it's on exactly, they tell us that if you rotate a symmetrical object about its center that is in this shape, then its moment of inertia is 1/12 the mass of the object times the length of the object squared. So all we'd have to do now is put our 0.2 kilograms, if that's the mass of the meter stick, times the length of the object, which is 1 meter, and square that times 1/12. All right, so this is the idea. So so we got a lot going on here, and you're actually going to get some practice with this in the lab. But you can see now that this idea of adding up moment of inertias is important for an object like this, where you have 2 point masses, right, of mr squared, and you have to know this formula, that it's useful to know that when you have a point mass, it's just mr squared, and when you have a meter stick, you either better know some calculus, or if you're not taking most of you will not take the calculus-based AP test for physics, and because this isn't a calculus class, what we're going to do is just give you this formula. And if we rotated this differently, if we move this axis of rotation out here, then this would be 1/3 ml squared, right? Because it's harder to rotate about this end. So the 1/3 would be larger than 1/12. All right, so hopefully that's making some sense here. And once again, we'll practice some of that in the lab. All right, let's do some examples. All right, this first example is from the book and in the chapter. Actually, all three of these examples are going to be from the chapter. But in this first one, what you have here is two objects that are made of the same masses, right? So M1 is 1 kilogram, M2 is 1.5 kilograms, M3 is 1.0 kilograms. And M1 is at the axis of rotation, but M2 and 3 are going to be rotated in a different way about this axis. So for the first instance, you can think of this as being somebody holding their arm up, right? And their hand is up by their head, and it's rotating about this axis right here, which is where the person is standing. So this would be the person's head, and this is their arm with their hand up by their head, and it's rotating around this axis. And the next example, and we'll call this axis A or object A, and object B or axis B. Now the axis of rotation is still at the person's shoulder, and it's going straight down through the person. But this time their arm is horizontal, so it's held out in front of them like this. And because of that, what's different here is the distance that R is from the axis of rotation, right? That in this case, R3 is from the axis of rotation. Mass 3 is closer to the axis of rotation, right? Because the axis of rotation goes straight through the person's body, right? And in this case, when it does that, this mass is further out from the person when their arm is held horizontally, right? And the axis of rotation is into the page, but it's still straight down through the person. This is almost like us standing above the person and looking down, right? And seeing this arm rotating horizontally. So the idea is that mass 3 is further away here, right? And that's what you have to know. Because these thin rods are each 10 centimeters. So this is 10 centimeters, this is 10 centimeters. This distance then is 10 centimeters, right? That M3 is from the axis of rotation. But over here, we can see 10 centimeters, and now M3 is further away. It's the hypotenuse, right? It's 10 squared plus 10 squared, which is going to be the square root of 200, which is going to equal 14.1 centimeters. So do Pythagorean's theorem there if that doesn't make sense. And so the idea is, well, how did the moment of inertia change, right? And these rods are thin rods, so we don't worry. When we say thin, what that means is we don't consider them as having mass or it's negligible, right? So we can think of the object here. Object A is consisting of M1, M2, M3, all at some distance from the axis of rotation. And object B is M1, M2, M3, all at some distance from the axis of rotation. But is their moment of inertia, IA and IB, different? And the answer will be yes, because M3 is further away. So when it's further away, is it easier to rotate or harder? Well, if I hold the pen like this and I rotate out the end, it's harder for me to rotate like this. And if I hold the pen right here, it's easier for me to rotate when the mass is closer. So by having mass further out, I'm expecting to make it harder to rotate. And if it's harder to rotate, well, then the angular acceleration should be less. So we would expect alpha equals, or I could start with torque equals I alpha, alpha equals torque over I. And if that's the case, then when this gets larger, this gets smaller. So we expect to have a larger moment of inertia when the acceleration is smaller. So what I'm saying is we expect that IB to be larger because it's harder to rotate this when M3 is further away. So let's go ahead and do the math then, right? And I'm going to go ahead and flip this over. We can go ahead and say IA is equal to M1 these are all point masses, right? Times R1 squared plus M2 times R2 squared plus M3 times R3 squared. And so then we can say the moment of inertia is equal to, I already figured out the masses. M1 is 1 kilogram. They're all different masses, but they're the same three masses in both cases. Now, here it gets tricky, right? How far is R1 from the axis of rotation, right? Axis of rotation is right here. R1 is at the axis of rotation, so it does not contribute any moment of inertia, because moment of inertia, it requires a distance from the axis of rotation, so this distance is just going to be 0, right? So we're going to go ahead and get rid of this. So mass 1 does not contribute to the rotational mass because the axis of rotation is right through it. Okay. And all right, so let's go ahead and get the second mass here, which is 1.5 kilograms. Distance is 10 centimeters. I'm going to go ahead and convert that, so 0.1 meters squared plus M3, which is 1 kilogram again. And distance here for object A is going to be 10 centimeters for M3 from the axis of rotation, right? Okay, so 0.1. All right, so we can then say that IA is equal to, I think I already did the math for these, so this is going to be 0 plus 0.015 units here are kilograms times, don't forget to square your meters. Remember, we only square the 0.1 here, right? So typing these into my calculator just to make sure. 0.1 squaring it gives us 0.01 times 1 is going to be 0.01 kilogram meters squared. All right, so there we have it here. Now we just add these two together. I think we can do that in our heads. 0.01 plus 0.015, 0.025. All right. Okay, so there we have the moment of inertia of object A. Let's go ahead and find the moment of inertia of object B. It's going to be the same one, but slightly different, right? So we can see here the same formula is going to apply. We'll take the mass of object 1, which is going to still be 1 kilogram, multiply it by 0 squared, because object 1, whoops, I don't know if you can see that, object 1 still has no distance from the axis of rotation, which is into the page right here, it's vertically. So this is 0. And we're going to go ahead and add that to the mass of object 2, which was still 1.5 kilograms. But now this is, and it's still going to be 10 centimeters away, or 0.1. All right, but now see for object 3, this is where it's going to be different, right? So we have the 1 kilogram mass that is object 3 times 0.141 meters squared. And so what that's gonna what's gonna happen there is we're gonna have IB then is equal to 0 plus this is gonna be the same here, right? So 0.015 kilogram meters squared. And this is going to equal, what's 0.141 squared? So that's going to be 0.019881, and we just multiply that by 1, so that's going to be our answer. So we're going to add that to 0.019881 .99, I guess. We can round, right? 0.01. Should I round? I probably want to just round that to probably just want to round that to 0.020, right? And just keep it there. Why don't we do that? All right, approximately 0.020. So now we can go ahead, units kg meters squared. We can go ahead and add these together. And IB then is approximately 0.035 kg meters squared. Definitely larger than the moment of inertia of object A. All right, so you can see how with 3 point masses, all we had to do was get the moment of inertia of each point mass using the formula I equals mr squared, and that I total is the sum of I1 plus I2 plus I3, and go from there. All right, let's look at the next example. All right, this next example deals with something called the caber toss, and what it is it's this it's one of these, it's a Scottish game where people take a tree and they toss a tree, and it's kind of like they got I guess it was like what lumberjacks used to do when they have to move a log. They think it was invented that way, that maybe they had to throw a log into a river, or I don't know, just it's pretty awesome. So what you do is you take this log that looks like a tree. It's like a 19-foot log, and you hold it in your hands, right? You pick it up and you run with it, like this, right? You run with it like this after you've picked this log up, and then you get to the line, and then you toss the log, right? And it lands like this and then flips over, and wherever it lands, this distance to the line is how far you threw the caber, right? So you got this 19-foot log, which is about 175 or 200 pounds, I forget, somewhere around there, and so it's pretty cool. So we're going to pretend that somebody ran with this log, tossed it, right, and it hit right here, and then is falling over and about to land on the ground. And as it's falling over, we see that its weight is going to exert a torque and cause it to accelerate, right? Because if there's a torque, there's an angular acceleration. And you should know that now, right? Because torque is equal to I times alpha, right? And so anytime we have a torque caused by weight, a perpendicular component of the weight, that we have an angular acceleration. All right, so this is kind of pulling together our lecture on torque now with angular acceleration. All right, so what's tough about this problem, and I think I'm going to have to redraw it because I didn't want to write on my note guide here. So I'm going to go ahead and do a quick drawing really quick. All right. Sounds quick. Okay, so we have the pivot right here, axis of rotation. What's annoying about this is they tell us that the angle the caber makes with the vertical is 25 degrees. That this angle is 25 degrees right here. And the reason that that's annoying, the caber is going to have its mass acting at its center of gravity for our idea of where the torque, or where the force acts, the weight acts, right? It acts at the center of gravity. But we know now that its mass is actually distributed throughout the caber. So when we use its mass, we're going to have to use a moment of inertia formula for an object rotating about its end. And we actually know that for a symmetrical long object like this. I mentioned it earlier that I is equal to not 1/12, but that's actually greater when it's about its end, so it's 1/3 ml squared. All right, so we're going to have to use that formula here in a second. But we can see that since its weight, let me see if I can grab another color, acts at the center of gravity, that this is going to generate a torque, right? This weight, or we can call this Fg, right, is going to generate a torque. And we know that because of the way the geometry works out, that if this angle here is, let me get another marker, is 25, right? Then this angle here is 65 because it's the complement, and this angle here would be 90, and this angle here would be 25, right? And if I extended this a little bit further, and drew the perpendicular component of Fg, right? And this component, I'll just draw it anyways, that this is the force component that is perpendicular. So my point here is that if this is 25, this is 65, this is 90, this is 25, this is 65, this is 90, this is also 25. And once you understand that, it's easy to find a solution for the torque, because you can calculate R, which is this distance, right, times F perp, right? R is, let me go ahead and draw that in. This distance is R. And it's clear that R is just equal to the length of the caber divided by 2, right? Because it's half the length of the caber. Okay. Good. Could we have used R perp here instead? Definitely. I think I'm sticking with F perp here because that's what the textbook does. So, but kind of tricky to figure that out. And maybe I'll work through this again using R perp just because I think it's easier. Okay, anyways, let's go ahead and solve here, right? I guess we might as well, let me do the drawing again for R perp just to show you. I want to do it now. All right, let's go ahead and, so if we had the same thing happening, let me see if I can draw this similarly. Oh boy, that was pretty rough. So if this is the pivot, and this angle here, ooh, that's supposed to be 25 with the vertical. That doesn't look like 25, does it? Apologize for that. Let me see if I can maybe draw that. Let's see where this goes. So let's say this is 25. Let's use our imaginations, and let's go ahead and say the center of gravity is right there. This drawing's terrible. All right, let me try that one more time. So we have the caber being right here, and this being 25 degrees, and this being our center of mass. That's a lot better. Okay. And this being our weight, or Fg, and this being R, and this being the pivot. I think we can see then that this, right, the distance, the shortest distance between the pivot and the force line, or the line of action, is R perp. And if this is 25, then this this would be 65, this would be 90, and this would be 25. All right, so what I'm trying to say is torque is equal to R perp times F, which is the weight, right? So we can call this Fg. And then therefore torque is equal to the hip sine what? Because this is opposite, right? So it's got to be sine 25. You see that? All right, so this is R sine 25 times Fg. And I think that's easier. I don't think the book showed it that way. I think the book showed it this way, but if we go back up here, now we say torque is equal to F perp times R, correct? Because we're going to use the perpendicular force where it's perpendicular to R. This is now creates a right angle there, right? Where F is perpendicular to the radial line, which extends out right here, right? And we can see that for this triangle, F perp is opposite theta. And so F perp is going to equal Fg sine 25, right? So I'm saying torque is equal to Fg sine 25 degrees times R. All right, so whichever way you use, does it matter? No, right? Check it out, right? Torque equals Fg times R times sine 25. Torque equals Fg times R times sine 25. The order doesn't matter there, right, that you multiply in. Okay, so very good. We got an expression for torque. All right, but let's remember this problem is asking, I don't think I ever said what it was asking for, maybe I did, is asking for alpha. So we have an expression for torque, we have an expression for moment of inertia. Alpha equals torque over moment of inertia. Yeah, all right. So let's go ahead and write that, right? So we're saying that alpha is equal to torque over I. All right. Torque is equal to, we just said it, Fg sine 25, FgR, right, times R, times the sine of 25. And remember, you can't just assume it's always going to be sine 25, because they might not have given you that angle. They might have given you the complement, right? So sometimes it's going to be cosine of the angle they gave you instead, or they just might have given you, the complement instead. So if that's the case, if we had the complement here, we would have to take the cosine of that angle, right? Because F perp is adjacent to that angle. All right. Good. Okay. I was just about to say, the sine 25 is equal to the cosine of 65, right? That's why sine has the letters CO in front of it, right? For complement. So it's cosine. I don't know if you knew that, but I'm sure you did. All right. Anyways, so coming back to this, let's go ahead and divide by the moment of inertia, which is 1/3, right? We said it a second ago. This has an infinite number of points, so we can't use a point mass for this. We can't say mr squared for this, right? Because there is more mass acting about this pivot than just the center of gravity, right? We have to, this is an extended object. That's probably the best way to think of it. And on the AP test, they will tell you, they'll be like, look, extended object, and that's like a flag, a red flag, to use a moment of inertia formula, or to consider the mass acting at different points and add up the different masses, the different moment of inertias using mr squared. All right, anyways, 1/3 ml squared. I like that I have an R here, or I don't like that I have an R and I have an L. So we're going to have to make that simpler. and maybe it's best if we just use L, right? So what I'm trying to say here is this is FG times 1/2 L, right? That's what R is, times the sine of 25. Now, all right. Okay, so right now, if this looks gross to you, you know FG, right? It's your mass, which is 79 kilograms times 9.81. And let me go ahead and rewrite this one more time then. This is getting kind of neat. mg, right? Okay, so we have two options here. The easy option is just to put numbers in now for everything. 79, 9.81, 5.9 meters, 19 feet, right? 5.9 meters, 79, 5.9 meters squared. I think a cooler thing to do here is just to simplify, right? It's way more fun. And because we can make this even simpler looking. We can first divide off the m's. And then we have an L on top and an L on bottom, so we can get rid of the L on top and get rid of one of the L's on bottom. So I'm going to go ahead and rewrite then. It's interesting here, I'm just thinking about this, that the mass of the caber does not affect its angular acceleration, right? That's what this is. This is angular acceleration. That's neat. So we wouldn't have saw that had we just put numbers in, right? Okay, fractions inside our fraction gross. Remember, we multiply by the reciprocal when it's on the bottom. So this is, what's the reciprocal of 1 over 3? You'd say 3 over 1. So the 3 is going to go up here, and the 1 will stay down here. Fractions, the 1 just stays up top, and the 2 just goes to the bottom. So long story short then, alpha equals 3g sine 25 over 2 goes to the bottom, 2 L. Okay, so we're saying 3/2 g sine 25 over L. Okay, so there's our expression that we have here. Let's go ahead and put the numbers in and solve, right? Let's find alpha. And remember, at the end, this is going to be in what units, right? Even though I'm in degrees right now, it's going to be in radians per second squared. Okay. I think we said this is 5.9 meters. Notice meters are going to cancel away, right? And that's where our radians are going to be there, right? The radians per second squared. Second squared is going to go to the bottom. All right. So anyways, let's go ahead and multiply this out a little bit, simplify. 3 times 9.81, 29.43 times the sine of 25. I think I'm still in degrees. I don't think I ever switched to radians. 12.438 approximately. In general, you don't want to round to the end of the problem, so I'm keeping this extra digit to help with that. 2 times 5.9. Okay, so I have this number divided by 11.8, so 12.437655. I'll just try and keep some of those digits. Divided by 11.8 is about 1.05 radians per second squared. All right. I'll go ahead and put the 4 there. 1.054. Whoops. This is rough to look at because I forgot to write 11.8 here. Okay. Let's rewrite that where I have some room. Alpha then is equal to 1.054 radians per second squared. All right. It is rotating. I was going to say, is it rotating clockwise or counterclockwise? It's rotating, speeding up this way, which is counterclockwise. So it's going to have a positive alpha, or positive torque, because counterclockwise is positive, so I don't need a negative sign here. But if you want to put CCW, you can, in that, or if you had to indicate direction. It's not a bad idea. All right, that's it. Let's go ahead and do one more example, and then we'll call it good here. Example 3, what we have here is a engine in a small plane is specified to have a torque of 500 Newton meters. So I'm going to go ahead and write that down. The engine drives a 2 meter long, so we know L is equal to 2 meters. 40 kilogram, M is equal to 40 kilograms. Single blade propeller. On startup, startup means our initial velocity is going to be 0. It's not spinning, right? And then we're going to give it this torque, cause it to start spinning, and it's going to reach a final angular velocity, they tell us, of 2,000 revolutions per minute. So we know that WF has to equal 2,000 revolutions per 1 minute. And we don't really like that, right? We like working in radians per second. So that's kind of ugly and gross for us for this problem. So we need radians per second because that's what we like. All right, so hint, the propeller can be modeled as a rod rotating about its center. So what we have is, if we have a rod rotating about its center, was it 1/12 ml squared or 1/3 ml squared? And hopefully by now you're starting to remember, well, it's easier, so therefore it's going to be the smaller moment of inertia, because when the moment of inertia is smaller, let's see, alpha is larger, right? When the moment of inertia is smaller, alpha is larger, so it's definitely going to be the 1/12 ml squared, right? So I equals 1/12 ml squared. And so you want to go ahead and look that up if you forget that formula, right? For a thin rod rotating about its center. All right. So anyways, there we go. I think we're pretty straightforward here. Let's get this. So what's the question? The question is, how long does it take? So that's asking for time, right? So we want to know t. So you might say, well, what's the connection here, right? Between say these three variables and these three variables. Can you see it? The connection is what? Well, this is a change in angular velocity over a time. That sounds like an acceleration, right? So we have another acceleration formula we're going to use in this problem. Our angular acceleration is equal to omega f minus omega I over t. That if we can find alpha, we can solve for t because we just rearrange, right? This goes here, this goes there. Just do the algebra. If that doesn't make sense to you, write that out and solve that, and make sure you're convinced that this is the same as this, all right? And so we just need omega f, omega I, and alpha. All right, well, you can kind of see where we're going, right? We know alpha is equal to torque over moment of inertia, so we can get that. And we know omega f is equal to 2,000 revolutions per minute, but I think we can change that to radians per second. So let's start by doing that, right? Let's say we have 2,000 rev per 1 minute. Well, first of all, we want radians, and we know that 1 revolution is equal to how many radians? 2 pi. All right. And we can cancel off our revs. And now we're in radians per minute. We want per second, so we need one more conversion factor. 1 minute is equal to 60 seconds. Cancel off our minutes. And we're good to go, right? We just do the math there. Let's see, 2,000 times 2 pi times radians divided by 60. So 2,000 times 2 pi, ooh, where's my pi button? 2 pi, just like that. 12,566.37 divided by 60 is equal to 209.44. 209.44. Remember what I said about rounding early. Try not to round that early. I just like to write that there so you guys can remember it and see it. But try to keep this number in your calculator and use this. All right, so anyways, radians per second. And this is equal to our omega f, approximately, right? All right, so let's get alpha. Now we have, because we have this now, and this can just get subbed into right there, but we need an alpha for here. So alpha is equal to the torque, which they were kind enough to just tell us and not make us calculate. And then I is equal to 1/12 ml squared. Ooh, maybe we should find I first up here. I then is equal to 1/12 40 kg times L is 2 meters. All right, so that's going to be I is equal to, what's that? I'll just do that in our calculator. 4/12 is 1/3. So I'm thinking 1/3 times 40. Yeah. All right, 40 divided by 3. 13.3 repeating. And that's going to be kg. I should use uppercase K. God, it's such a bad habit. All right. Okay. And now we can sub that right there, right? All right, notice our meters, we're going to end up with newtons divided by kilogram meters, which is going to give us per second squared on bottom, and it's going to be radians per second squared. All right, so let's take the 500 divided by 13 point, I don't know how to do 3 repeating, so I'm just going to type in a bunch of 3s like that. Good times. All right. 37.5, almost exactly, right? I bet if I had 3 repeating, it would be exactly. So, all right, 37.5. Units for angular acceleration, radians per second squared. We're going to plug that in. Oh, we're going through this one right there. All right. So you can see now the logic. So we're going to get, oh, and we know omega I is equal to 0. Oh, this is confusing. If you watch the video, though, the whole video, it will make sense. But omega I goes there, omega F goes there, alpha goes there. All right, that's what all those arrows are trying to say. And we can solve for t. So let's go ahead and finish this up. So we're saying, try and get this a little more organized. T is equal to omega F, which we said is 209.44 radians per second minus 0 divided by alpha, which is 37.5 radians per second squared. So at the end here, we're going to get seconds for units because we'll have a seconds on the bottom of the fraction and it floats to the top. 209 divided by 37.5. Oh, that's going to be a nice number. All right, 20. And it should be, right? I mean, it's how many seconds does it take the propeller to get up to speed? All right, 209.44 divided by, I don't know if you can see that, 37.5. 5.585. And units here should be seconds. All right, and that's it. So hopefully this is making sense. And these examples are nice, but you have to realize that not only what makes them difficult is that we're taking these new ideas, right? Alpha equals torque over I equals some formula, alpha equals omega F minus omega I over T, and then giving you a story problem where you gotta find your variables and then apply them to these formulas. So that's what makes these problems difficult. If it was just solve for alpha, solve for I, solve for alpha this way, right, then it would be easy. What makes this tough is that it's a story problem and you got to figure out what the heck it's even asking. It's asking for time, and then how to go about doing it, right? Based on this plethora of variables you get, right? So how you would go about doing it, which isn't easy. So anyways, hopefully it's making more sense, and we'll call it there for the lecture. All right.